Good evening, student. So today we'll discuss constraint optimization method. We have already discussed the penalty parameter approach and how to handle for handling constraint using penalty function. But today we'll discuss about the necessary and sufficient conditions for optimality in case of constraint optimization problem. So as we have discussed, that general formulation of an optimization problem is either the function is a minimization or maximization function. So I have written here minimization oblique maximization of a function of multivariable function, that is we have up to n variable, and then the problem is subjected to two types of constraint. So one is equality type constraint and another one is inequality constraint. Okay, so we have equality type constraint. That means we have the equality sign and inequality sign. So we'll discuss one by one. So initially we'll discuss the problem with equality constraint. That means we will only consider the ZJX. Okay, so we'll only consider this one, and then we'll also discuss in the next class. We will discuss a problem with inequality constraint. So as I said, the problem with equality constraint, so I can write it minimization or maximization of fx and subject to zj x equal to 0, and we have total m number of your constraint. Okay, so we have total m number of constraint, and it's a multivariable problem, so therefore we have up to n variable. Now if I plot it, suppose if I plot the function, so this is an any arbitrary function. So this is basically I have plot the contour plot for fx. So this is basically I have plot for fx, yeah. So for fx, and now what is the minima here? So the minima here is somewhere here. Okay, so this is the minima of this particular function. Okay, so this is the minima of this particular unconstrained function. That means if I try to minimize your fx, then I should get this solution, so where the first derivative is equal to 0. So this is the minimum of this function. Now if I plot the zx, okay, so gx is is your constraint, and this is a equality type constraint. So therefore what does it mean? The solution must be on this particular line. Okay, so solution must be on this particular line. So in the last class I said that if the constraints are not satisfied, suppose I get a solution. So earlier solution is this, and maybe I can say that this is your this particular point is x1 star and y is so y1 star or x2 star basically. Okay, so x1 star and x2 star. Now if suppose for the constraint optimization problem, so this point must be on this particular line. If it is not in that line, on that particular line, then what we'll say that the solution is not a feasible solution. The solution is not a feasible solution in that case. Okay, so therefore the earlier solution, which is x1 star and x2 star, so that was the optimal point for unconstrained optimization problem. So that is now not a feasible solution. Okay, so that is not a feasible solution because that solution is not satisfying the constraint. Okay, so therefore now this is not the minima of this constraint function. Okay, so this is not the minima of this constraint problem, and basically so new minima may be somewhere here. So this is the minimum point, and basically this will also satisfy this constraint. So earlier minimum point was here and new minimum point is here, so this may be the minimum point. I hope this is clear to you. So I would like to find out what is the minima of this constraint optimization problem. Okay, so that is the your objective of, and we'll try to find out the sufficient and necessary condition for optimality in case of your constraint optimization problem. And right now we are discussing equality constraint. Now let us discuss discuss a problem with two variables. Okay, so two variable problem. So let us discuss a problem with two variable. Okay, two variable problem. So this is again, so I can write it. This is in that case, if it is two variables, so minimization or maximization of f x1 x2. So I have now two variables, so that is your x1 and x2, and then I have only one constraint, that is z. Okay, so if you have multiple constraint, then you will have z1, z2, z3 up to zm or z sub to k, something like that. But let us discuss for two variables and one constraint, that is your, I have only one constraint, that is z x1 x2 equal to 0. This is the equality constraint. So if I plot it, then so this is the function fx, so this is the function fx. Okay, so this is the function fx, and this point is basically, suppose I am getting this particular, okay, this is the point, and which is basically x1 and x2. Now if I take a derivative of the objective function, so as per the necessary condition, the derivative should be equal to 0 at optimal your point. Okay, so at optimal point derivative is 0. So if I take the total derivative, which is equal to del f by del x1 into dx plus del f by del x2 into dx, and that must be equal to 0 at basically, so this is equal to 0 at x1 star and x2 star, that is the optimal point, so that must be equal to 0. Okay, so this is basically coming from the necessary condition for optimality. Okay, the first derivative should be equal to, total derivative should be equal to 0. Okay, so here total derivative is 0, so that means the partial derivative is 0. Del f by del x1 is 0 and del f by del x2 is 0, because dxn and dx2 are not 0, so these two should be equal to your 0. So if x1 star and x2 star is the solution of the constraint problem, then what will happen? If this is the solution, then it must satisfy this constraint. That means that must be on the z line, and that is therefore zx1 and x2 must be equal to 0. So basically you were at this particular your point. Now what will happen? So it may be at any point, suppose you are here or you are here or you are here, so in any point, but this must be equal to 0. That means z x1 x2 must be equal to 0. Otherwise what we will say, that the solution is an that particular solution is not a feasible solution, because it is not satisfying the constraint. Okay, so now any deviation dx1 and dx2 is admissible only when that this is again if I dx1 and dx2, that means I am getting in new points, that is x1 star plus dx1 and x2 star plus dx2. So it is admissible, that means only when that it is also 0. It is also 0 means it is on that particular constraint. Okay, so therefore what does it mean? That it is, suppose you are here, so you can move along this line basically, so you can move along this line, but you cannot move along, suppose this is a point D, so you cannot move along the D line. Okay, because once you're moving along this line, so that means you are moving to the infeasible solution. Okay, so you are moving towards the infeasible region, so that means you must move along this particular line. So maybe I can move slightly on this, in this direction or on this direction dx. Okay, so in that case only that z, so that is the admissible movement, so you can allow movement along that particular line. That means you are searching the solution along that particular line of or along that particular constraint. So that means, so what does it mean? Whatever new solution, okay, so you're trying to search, so new solution x1 star plus dx and x2 star plus dx2 should be equal to 0. Okay, so therefore I can expand it. What does it mean? I can expand it using Taylor series. Okay, so in that case this will be z x1 x2, then del g by del x1 dx1 and del g by del x2 dx2, and that must be equal to 0. So I'm not writing the higher order derivative, I have just expanded up to your first derivative, and that must be equal to 0 in that case. So if I expand it using your Taylor series, now this must be equal to 0 because z x1 star and x2 star is a feasible solution and it is on that particular line. So therefore this is equal to 0, and if I put that this is equal to 0, then what I'm getting, so this is nothing but the total derivative of function z at your x1 star x2 star. So I can write that dz, which is equal to del g by del x1 dx1 plus del g by del x2 dx2. So this must be equal to 0. Okay, so this must be equal to 0. So I'm getting it. So now if I put, so if I just if I rearrange and these terms and try to find out the value of dx2, so in that case what I'm getting, dx2 is equal to minus del g by del x1 del g by del x1 divided by del g by del x2 dx2. So I am getting a relation something like that. So what does it mean basically? If I move your x1 along dx, it means x1 by dx, so in that case the dx2 dx1, that dx2 value should be like this. So automatically I can calculate what is the possible dx2 value. Okay, so possible dx2 value, and basically I have to move along that direction, otherwise I will be moving towards the infeasible region. Okay, so that means if I move along, suppose if I move along x direction, so dx2 must be something like this. So if I move along x and this is basically dx1, and this will be your dx2. Okay, so you are moving towards dx2, then only you will be at that particular your constraint. Okay, so therefore I'm getting this, yeah, I am getting this relation. So therefore any movement dx1, I have to calculate dx2 using this equation. So now so I in the previous slide I got this. So dx2 equal to minus del g by del x1 divided by del g by del x2 dx1, and then putting in the necessary condition for optimality of the objective function, that is df equal to del f by del x1 dx1 plus del f by del x2 dx2, which is equal to 0. So now you replace dx2 using this equation. Okay, so if you replace it, then what I am getting, del f equal to del f by del x1 dx1 minus, so I am putting del f by del x2, and in place of dx2, so I am putting del g by del x and del g by del x2 dx2. So this is basically at x1 star at x2 star. Okay, so that is basically at the optimal point. So at optimal point this must be equal to 0. Okay, so remember that what we are trying to what we are trying to do it here, that we are trying to find out the necessary condition for optimality in case of constraint optimization. So therefore at basically optimal point, so df is equal to 0. So finally I am getting df equal to this, and then if I rearrange this your terms, so I'll be getting del f by del x1 then into del g by del x2 minus del f by del x2 into del g by del x1 dx1, and therefore the criteria, the necessary condition is that dx1 is not 0, so therefore this must be equal to 0. Okay, so this term must be equal to 0. Okay, so I'm getting del f by del x1. I'm getting del f by del x1 into del g by del x2 minus del f by del x2 into del g by del x1, and this is the basically criteria for optimality in case of constraint optimization problem. Okay, so this is the necessary condition for optimality for optimization problem with equality constraints. So we have actually what we have done, we have actually derived this equation for equality constraints. So as I said, the inequality constraints, so we will discuss in the next class. Okay, so let us discuss the Lagrange multiplier method. Okay, so this method is, so again we'll discuss about the same problem with two variable, that is minimization or maximization of f x1 x2 subject to z x1 x2 is equal to 0. So what I can do basically, so we have already derived that we have already derived the condition at optimal point. So that is del f by del x1 minus del f by del x2 into del g by del x1 divided by del g by del x2 is equal to 0. And if I rearrange these things, del f by del x1 minus del f by del x2 divided by del g by del x2 into del g by del x1 equal to 0. And if I put that this is equal to lambda, okay, del f by del x2 divided by del g by del x2, that is negative of del f by del x2, and del g by del x2 is lambda. So in that case I can basically write that del f by del x1 plus lambda del g by del x1 equal to 0. Okay, so this is the condition I am this is the condition I am getting. And similarly I can also write that suppose if I write in terms of del f by del x2, so then I am getting del f by del x2 plus lambda del g by del x2 equal to your 0. And so these two condition has to be satisfied. Okay, so this is coming from the optimality criteria, that is del f by, so yeah, in terms of x1 if I write del f by del x1 plus lambda del g by del x1 equal to 0, and in terms of x2 if I write del f by del x2 plus lambda del g by del x2 is equal to your 0. And at that point, and this point, whatever solution you are getting, it must be on that particular equality constraint. So therefore z x1 x2 should be equal to 0. Okay, so what we are doing basically, from the optimality criteria we are trying to derive this, we have derived this equation. So these three equation we have derived, and this equation are the necessary condition for optimality. Okay, so these equations are the necessary condition for optimality. So basically I'm getting the necessary condition. Now this equation can also be derived using the Lagrange function. The same equation I can derive using this method. So let us define a Lagrange function now. Okay, so now lambda is also coming. So now it is the L is a function of x1 x2 and lambda, and which is equal to f x1 x2 plus lambda, so lambda z x1 x2. Okay, now this is known as Lagrange function. So this is basically Lagrange function. Okay, so this is Lagrange function. And if I apply the necessary condition of optimality, in the first, I think in initial classes we have discussed what is the necessary condition. The necessary condition is the derivative with respect to the variable. Okay, so now it's a three variable problem, x1 x2 and lambda. So derivative with respect to x1 x2 and lambda should be equal to 0. Okay, so therefore what is the necessary condition? That you take derivative with respect to x1. So I am getting del f by del x1 plus lambda del g by del x1 equal to 0. If I take derivative with respect to x2, then del L by del x2 equal to del f by del x2 plus lambda del g by del x2 equal to 0. And if I take derivative with respect to lambda, so then I am getting z x1 x2 equal to 0. So you just see these are the three equations which we have already derived. Okay, so from the criteria for your optimal means the criteria for optimality, and now we are getting the same equation. Okay, so these are the necessary condition for optimality. Okay, so I'm getting, so you are taking, you are applying the necessary condition for optimality, so I'm getting these equations. Okay, so therefore the sufficient condition for optimality of a Lagrange function, okay, can be written as, so what is the sufficient condition? I think you remember that for sufficient condition, if it is more than one variable, okay, so for multivariable problem, what we are doing, we have to calculate the Hessian matrix. That means the second derivative we have to calculate. So that will be a matrix, and this is a Hessian matrix. So Hessian matrix, so I can calculate this is second derivative. So first term is del square L by del x square, then del square L by del x2 del x1 del x2, and this is del square L by del x1 del lambda. Okay, so similarly I can also write the other terms. So this is the Hessian matrix, and if I simplify it, so what I will be getting, so I am getting, so this portion is basically the unconstrained, it's coming from the unconstrained it's coming from the objective function, that unconstrained function, and these additional terms are coming from the your equality constraint. So what you are getting, del g by del x1, del g by del x2, similarly this is del g by del x1, del g by del x2, and this term is equal to 0. So now this is the Hessian matrix. Now what you have to do, I think you know what you have to do, that you have to determine whether this Hessian matrix is a positive definite matrix or negative definite matrix, or neither positive nor negative. So if it is a positive definite, then what will happen? If it is positive definite, then that whatever solution you are getting, that is a minima. Okay, if it is negative definite, then what you are getting, that whatever solution you are getting, that is a maxima. If it is neither negative nor positive, then this is a saddle point. So it is neither positive nor if it is neither positive definite nor negative definite, then in that case that is a saddle point, and you are neither getting that is not a minima, or means neither minima nor maxima. I think you know that one. So only thing is that I have to calculate the Hessian matrix, and I have to see whether this is a positive definite matrix or negative definite matrix. Okay, so this is the sufficient condition for optimality in case of constraint optimization problem. So again, so I have just written the same thing, that if H is positive definite, the optimal solution is the minimum point. If H is negative definite, the that optimal solution is a maximum point, and else it is neither minima nor maxima. So now let us see the Lagrange multiplier for generalized function. Okay, so whatever we have discussed, it is only for two variable and one constraint. Now if you want to write it for multivariable, suppose you have a variable up to n, x1 x2 x3 up to n variable, and we have actually m constraint. Okay, so m constraint, that means z1 z2 z3 z4 z5 like that up to zm. So it's a multivariable problem with multiple constraint, multiple equality constraint. Again, whatever we are discussing is for equality constraint. So multiple equality constraint and multivariable your problem. So then I can write the Lagrange function like this. So Lagrange function will be L x1 x2 up to xm, and now we have more than one constraint, so therefore every constraint there will be a Lagrange multiplier, that is lambda 1 lambda 2 lambda 3 up to lambda m. and so I'm writing this is fx, and then lambda 1 g1x, lambda 2 g2x, and up to lambda m gmx. Okay, so you are basically adding all these three, all these your constraint function. So what is the necessary condition? The necessary condition is that the partial derivative with respect to each of the variables should be equal to 0. Okay, so therefore I'm writing like this, that is del L by del x1 plus del F by del L by del x1 equal to del F by del x1 plus summation of, now for all the constraints, so I have to write that lambda j. So lambda j is coming out because this is the constant here, and because we are finding the derivative with respect to x. Okay, so lambda j and del j by del xi. Okay, so this is basically, and you are adding all those things, and so how many equations you are getting? So you are getting total n equation, because x is varying from 1 to n equation, so you are getting. And similarly then you take the derivative with respect to lambda j, and so you are getting zjx. So how many equations you are getting? You are getting total number of equation here is your m, up to m. So in this, how many equations you are getting? Here you are getting n equation, and here you are getting m equation. So total equation is n plus m. Okay, so total equation is n plus m. Okay, so total equation is n plus m. Okay, so this is the number of equation you are getting. So now you can solve this equation, and you can find out the value of your x1, x2, then lambda 1, lambda 2, lambda up to lambda m. So all these values you can find out. So now what is the sufficient condition? So similarly I can also derive the Hessian matrix. Okay, so now Hessian matrix will be so this is basically for the objective function. So this is, and other things are coming due to the constraint. Okay, and this part will be equal to 0. Okay, so this part will be equal to 0. So here, so I'm defining here what is Lij. So Lij is del square L by del xi del xj. Okay, so here this is 1 1, so therefore this is del square L by del x1 square, and this is del square L by del x1 del x2, something like that. And what is Zij? Zij is del gi by del xj. Okay, so you can find out the Hessian matrix. So this is the for your n variable and m constraint. So I can write the Hessian matrix like this. And once you are getting the Hessian matrix, so find out whether Hessian matrix is a positive definite, negative definite, or otherwise, and you can actually tell whether that is a minima, maxima, or an or neither minima nor maxima. Now let us see, suppose there is a constraint, and which is basically zx equal to b. Okay, so I'm taking one constraint, zx equal to b. Now suppose if there is if b is changing by delta b basically. Okay, so then how basically it will influence the optimal solution. Okay, how optimal solution will change in that case basically. Okay, so that we are trying to find out here. So the Lagrange function, suppose in this case the means minimization or maximization of fx. So now I have n variable, and basically I can write that gx equal to b, or I can write b minus gx equal to 0. Okay, so if I apply the necessary condition, so what is the necessary condition? The necessary condition is del f by del xi plus, now this is the constraint function. So now this is the constraint function, and basically you are trying to find out lambda del g by del x. Okay, so in this case, if I take the derivative of this one, so what I will be getting, this is negative of del g by del your xi. Okay, so I'm writing, so this is the negative value, so that is del f by del xi minus lambda del g by del xi equal to 0. And and if I take the derivative of with respect to lambda, then I'm getting b minus z equal to 0. So these two are the necessary, these two equations I'm getting by applying necessary conditions. Yeah. So from here, I can write from this equation, I can write it that del g by del xi, which is equal to del f by del xi by lambda. Okay, so I'm getting this your equation. Okay, now further, if I take the derivative, the change in b minus change in d should be equal to 0. That means db minus dz should be equal to 0. So if I take the from the constraint function, so from the constraint function, so I should get it. Then what is db? db equal to dz, and dz means the total derivative of your z. So I can write it when I have n constraints, so it is I2 means I2 n, so del g by del xi. So this is actually total your number of variables is your n in that case, so summation of del g by del xi dxi. And so now if I put, that is what is this thing, that del g by del xi is nothing but del f by del xi by lambda. So I'm putting 1 by lambda del f by del xi dxi. So I'm just replacing this term by your this term. Okay, del f by del xi by lambda. So I'm getting db equal to summation of I equal to 1 to n 1 by lambda del f by del xi dxi. So I'm getting this one. And so what is this now? This is if I take lambda out. So if I take lambda out, then what I'm getting, if I take lambda out, so I'm getting that this is summation, and this is del f by del xi, this is dxi, and this is I equal to 1 to n. So this is your df. Okay, so this is your df, total derivative of f. Okay, so if I put df, then I'm getting db equal to df by lambda. Okay, or lambda equal to df by db. Okay, so what does it mean basically? That I can actually find out what will be the change in optimal function value, by that if there is a change in constraint, that is the constraint value by db. Okay, so the change that constraint value is changing by db, then I can find out what is the value of df, so depending upon this lambda. So therefore, that suppose if I look at this particular equation, then what lambda is telling basically, so lambda is telling that if there is a change in the objective function, then how basically it will change the your overall optimal solution. If lambda is, suppose lambda is 0, so lambda value is 0, what does it mean? That means that if there is some change in the constraint, okay, so if there is a change in the constraint function, that means b value is changing. Okay, so in that case it doesn't have any influence in the optimal solution, so optimal solution will not change if there is a change in del b. Similarly, if lambda, so I have written here, so lambda star may be greater than 0, lambda star is basically less than 0, and lambda star is equal to 0. There may be three conditions, so whatever lambda value I am getting, so now if lambda is greater than 0, then what will happen? If there is a positive sense in your B, there will be a positive sense in the optimal your function value. Okay, similarly, so it's a direct relation. There is a positive sense, then there will be a positive sense in DF. But if it is less than 0, then what will happen? If there is a positive sense in these things, so there will be negative sense in your optimal function value. Okay, and if lambda star is equal to 0, so it means that particular constraint is not sensitive. If there is any sense in the dB value, then there will be corresponding sense in the objective function is your 0. There will be no sense in the optimal function value. Okay, so therefore now I think you will appreciate what is lambda basically. So lambda is also telling that how this constraint function is influencing the optimal solution. So therefore, if suppose lambda value is very high, so in that case what will happen? Suppose you are getting a optimal solution of a constraint optimization problem. Okay, now question is that suppose it's a design problem. Okay, and there is a constraint, and for that particular constraint the lambda value is very high. It's not 0, it's very high value, or it's not a small value. Then what you have to do basically, you have to be very careful in implementing that particular design, because if there is a small sense in that particular constraint, the corresponding sense in the optimal solution will be very large. Okay, so optimal function value will be very large. So therefore, when you are implementing that particular your design parameter, so you have to see that that particular constraint is totally satisfied. So there is no, but in some cases, suppose lambda value is very small, okay, you can be relaxed a little bit, because if there is a small sense in the constraint function, okay, so that that B value, so the corresponding sense in the objective function value is minimal, so that is not very sensitive. But if it is 0, then I think you can relax, so you can do that if there is some sense, and the corresponding sense in the optimal function value is not there. Okay, so therefore, so lambda is also giving some information that how this constraint or constraint function is influencing the optimal function value. Okay, I hope this is clear to you. So now let us solve this problem. This problem is find the maximum of the function fx, that is the function is fx equal to twice x1 plus x2 plus 10, and subject to gx, which is gx equal to x1 plus twice x2 equal to 0, using Lagrange multiplier method. So you have to use Lagrange multiplier method, and also find the effect of changing the right hand side of the constraint on the optimal function value. Okay, so this you have to find out. So I can write it something like this, that is f of x1 and x2, which is equal to twice x1 plus x2 plus 10, then z x1 x2, which is equal to x1 plus twice x2 squared, x2 squared equal to 3. So I can write it like this. So this is 3 minus x1 minus twice x2 squared, and which is equal to 0. So if I write the Lagrange function, so Lagrange function will be x1 x2 and lambda, which is equal to fx. So this is fx plus lambda gx. So fx is twice x1 plus x2 plus 10, and then I'm writing plus lambda 3 minus x1 minus twice x2 square. Okay, so now you find out the necessary condition, that is your del L by del x1 equal to 0, del L by del x2 equal to 0, and basically then del L by del lambda is equal to 0. Okay, so if you write this one, then what you are getting, you are getting this is 2 minus lambda is equal to 0. So from here I can get that lambda equal to 2. So from here I am getting 1 minus 4 lambda x2 is equal to 0, and then I'm getting x2 equal to 1 by 8, okay, which is equal to 0.125. Okay, and here I'll be getting 3 minus x1 minus twice x2 equal to 0, and if I solve it, then I'm getting that x1 equal to 95 by 32, which is equal to 2.97. Okay, now what you have to do, you have to find out the Hessian matrix. Okay, so calculate the Hessian matrix. So in this case, if you calculate the Hessian matrix, so you should get 0 0 minus 1, then 0 minus 4 lambda minus 4 x2, and this is minus 1 minus 4 x2 0. Okay, so put the value at that is your x1 star equal to 1 by 8, sorry, x1 star equal to this is this is 2.97, and x2 star equal to 1 by 8. Okay, so if you put it, then you are getting this is 0 0 minus 1, then 0 minus 8 minus 0.5, and this is minus 1 minus 0.50, and if you find out the your positive definite, so this is the positive definite matrix, and therefore the solution is your minima. Sorry, this is a negative this is a negative definite matrix, so this is this is a negative definite matrix, and therefore the solution will be your that whatever solution you are getting, that is a minimum point. Okay, so you can find out. So here the eigenvalues, so you are getting the, if I calculate the eigenvalues, so lambda, don't you're confused with this, lambda is the eigenvalue, so or I can write that this is your eigenvalue lambda I or something like that, and this value is coming 0.6 sorry, this is coming minus 6.2972. so therefore the matrix is the negative definite matrix, and then whatever solution you are getting is basically then, so x star, that is your x, that is your the point, this is 2.97, and 1.8 is a maximum. Okay, so that you are trying to find out, and similarly I can also find out what is, suppose if there is a small change in dB, so we have obtained that df equal to lambda dB, so I will be getting that df equal to twice dB, so if there is a small change, suppose negative change, that means 2, suppose 1 unit change, so objective function value will change by 2, and basically, and similarly, if suppose this is your positive change, so in that case objective function will also your change positively. Okay, so therefore I can also find out, so here the lambda value is your 2, that means if there is a 1 unit change in your dB value, the corresponding change in the objective function value will be 2 units. Okay, so I hope this is clear to you. So let us stop here. So maybe you can solve another problem. So today I will give you another problem, so you can solve it. And if you have any question, yeah, you can ask, or you can ask me. Okay. So thank you very much. Please solve it again. Okay. So please go through the lecture note and try to solve some other problem.